So today I want to come back to the so-called stability circles. I here sketched some circles in the load plane, and we saw as soon as our load admittance comes out of the circle, then the input admittance would be negative. So for example, here the stability circle lies totally in the right half plane. This means if I have a positive load admittance, this positive load admittance will result in a negative input admittance. So we saw, with the help of the simulation, we saw that the stability circle can move in the load plane, and especially we saw that it may also move into the left half plane. And now I want to discuss this again, because, for example, here this stability circle, part of the stability circle lies in the right half plane, part in the left half plane. Of course, if I connect any of the load admittances, they will result in a negative input admittance, but we have here the point that only this part of the circle lies in the right half plane. That means a positive real part of the load admittance will result in a negative input admittance, but if I have the part of the left half plane, then only a negative load admittance would result in a negative input admittance. So we can say only this part of the stability circle is really crucial. Then only in this part of the stability circle a positive real part will end up in a negative real part of the load admittance. So as soon as the stability circle moves totally into the left half plane, then of course only negative load admittances would really result in a negative input admittance. And we can now see if the stability circle moves more and more in the left half plane, then in principle we can say in this point this is not very crucial. And as a condition for this we can say, of course, if we have that minus G center in the load admittance, so you see as soon as the center moves into the left half plane, the center becomes negative, so minus GL would be positive, and as soon as this is greater than the radius of our stability circle, we will have in principle no problems, but this results then in plus G22 plus real part of y12 times y21 divided by 2G11. This must be greater than y12 times y21 divided by G11. And as soon as we assume that G11 is greater, or we always assume this, we get that 2G11 times G22 plus the real part of y12 times y21, this must be greater than the absolute value of y12 times y21. Of course, also this part is positive, so we can divide it. So we will end up in 2G11 plus G22 plus real part of y12 times y21 divided by y12 times y21. This must be greater than 1. And normally one defines this to be K, the stability factor. So we say K is our stability factor, and as soon as K becomes greater than 1, our transistor is in principle stable. This we will also check with the help of the simulation too. So unfortunately during the derivation I did a small mistake. Here we must have a negative sign, and here also we must have a negative sign. So also here we must have a negative sign. That means the K parameter is now defined by this equation with a negative sign here. But as I already said, as soon as K is greater than 1, our transistor is stable.